And now we move on to the examples part of our discussion on temperature and heat. So consider the following problem. At 20 degrees Celsius, a brass cube has edge length of 25 centimeters. What is the increase in the surface area when it is heated from 20 degrees Celsius to 75 degrees Celsius? The coefficient of linear expansion of brass is 19 times 10 to the negative 6 per Celsius degree. As we can see from the problem, we are given the initial temperature 20 degrees Celsius and the final temperature 75 degrees Celsius. And it is always good practice to convert your temperature to Kelvin. So you have initial temperature in Kelvin and final temperature in Kelvin. We are also given the initial edge length of the brass cube, 25 centimeters, L naught, as well as the coefficient of linear expansion of brass, 19 times 10 to the negative 6 per Celsius degree. There are two ways of going about solving this problem, and we'll cover one of those ways. From our geometry, we know that the surface area of a cube is given by 6L squared, where L is the edge length of the cube. Knowing the initial edge length of the cube, 25 centimeters, we are able to calculate the initial surface area of the cube. And now performing linear expansion calculation, delta L is equal to L naught alpha delta T, where delta L is equal to final length minus initial length. We are able to calculate the final edge length of the cube, 25.026125 centimeters. And from there, 6L squared, we are able to calculate the final surface area of the cube. Knowing the final surface area, as well as the initial surface area of the cube, we are able to calculate the change in surface area of the cube. Alternatively, we can use the equation for the area expansion analysis. Delta A is equal to A naught sigma times delta T. But for that, we need to get the initial surface area. And as you can see from our solution, we can easily calculate the initial surface area using initial edge length L naught. A naught is equal to 6 L naught squared. So from there, we can easily calculate the change in surface area delta A. And now on to the next example. A copper slug, whose mass is 75 grams, is heated to a temperature of 312 degrees Celsius. The slug is then dropped in a glass beaker containing 220 grams of water. The glass has a heat capacity of 45 calories per Kelvin. The glass and the water both have an initial temperature of 12 degrees Celsius. The specific heat of copper is given 0.0923 calories per gram Kelvin. Assuming that the water does not vaporize when it comes in contact with the slug, determine the final temperature of the system when it reaches thermal equilibrium. So here you have basically three objects, the copper slug, the water, and the glass beaker. And so we have the following values. Mass for the copper slug, Mc, is 75 grams. Mass of the water, Mw, is 220 grams. We are given the specific heat of copper, 0.0923 calories per gram Kelvin. And You should already know or memorize the specific heat of water. In any case, here it is, 1 calorie per gram Kelvin or 4,187 joules per kilogram Kelvin. Again, it is advisable that you memorize the values associated with water. Specific heat of water, boiling point of water, freezing point of water, and so on. The same goes for air. We are also given the heat capacity of the glass, 45 calories per Kelvin. Note that heat capacity is different from specific heat. Be able to tell whether the problem is mentioning specific heat or heat capacity. And we have the initial temperature of the copper slug, 312 degrees Celsius. And for the water and the glass beaker, they both have the same initial temperature, 12 degrees Celsius. Now, when it comes to analyzing this problem, we use conservation of energy, which tells us that the total energy, in this case heat energy, the total heat energy of the system cannot change. It is constant. That is to say, change in energy is equal to 0. So any energy loss is counterbalanced or balanced out by gain in energy. In this case, heat loss and heat gain are cancelled out. So heat gain plus heat loss is equal to 0. So again, heat gain plus heat loss is equal to 0. Each object in the system, the water, the glass beaker, and the copper slug, we look at the heat gain and the heat loss of each object. So as you can see, in the heat gain part, you have QC, QW, and QG. So that's QC for the copper slug, QW for the water, and QG for the glass beaker. And the same goes for the heat loss. We have QC, QW, and QG for the heat loss. So we look at each object and see if if each object will experience heat gain or if the object will experience heat loss. So first, looking at the heat gain part of the equation, the copper slug will lose heat because it has a higher temperature than the water and the glass beaker, and you will recall that the normal flow of heat is from hot temperature, from higher temperature to cold temperature or to lower temperature. So the copper slug will experience heat loss, whereas the water and the glass beaker will experience heat gain. Moving now to the heat loss part, we zero out QW and QG because the water and the glass beaker will gain heat. It will not lose heat. They will not lose heat. It will be the copper slug that will lose heat. Each object will experience change in temperature. The conditions for phase change have not been met. So there's only temperature change in this situation. So you have QW giving you MC delta T, where and QG, since heat capacity is given, you have C delta T, and then QC you have MC delta T. Plotting in the values, you see that the only unknown in the equation is final temperature. Isolating TF, you are able to calculate the final temperature. There's only one final temperature for all three objects, since the system is in thermal equilibrium. And that's it for now. We'll continue our discussion of examples of temperature and heat in the next video.